Today is a review session for Exam 3. Exam 3 will be conducted from this Wednesday to this Friday. The format of the exam is the same as Exam 1 and Exam 2, online through the Man-Chung system. And the exam lasts 105 minutes. Exam 3 is open to the textbook and to your notes. And you can have a calculator. However, you must complete the exam on your own without any help from others. Exam 3 covers these 9 sessions in the book. How to prepare for Exam 3? I suggest that first, try the corresponding optional practice exam on Man-Chung. Second, try the past Exam 3 that I post on Wild Course. The third, review your Man-Chung homework and your written homework. Now, in the following, I present my solutions to Exam 3 in Spring 19. This is Exam 3, Spring 19. Problem 1. Air is pumped into a spherical balloon at a rate of 20 cubic cm per second. The question is, how fast is the radius of the balloon increasing at the instant when its radius is 50 cm? Initially, when time is 0, the radius of the balloon may or may not be 0. I don't know. Because the volume of the balloon is increasing, there must be some instant when the radius of the balloon reaches 50 cm. Now the question is, what is the instantaneous increasing rate of the radius at that instant? Here is a diagram about the balloon. I let R denote the radius of the balloon and V the volume of the balloon. Because the volume is increasing, R and V both are variables. They are changing. They depend on the time t. So they are functions of time t. The increasing rate of the volume is 20 cubic cm per second. That means derivative of V with respect to the time t is 20. The question is, how fast is the radius of the balloon increasing at the instant when the radius is 50 cm? To answer this question, we need to compute the derivative of R, the radius, with respect to the time t. Then evaluate the derivative at R is 50. A relation between R and V is the spherical volume formula. Take derivative with respect to the time t on this equation, then we have this equation. Move the constant 4/3 times prime outside this derivative, then we have this equation. Apply the chain rule to this derivative. Write this derivative into the product of these two derivatives. If you cancel dr, then the product is this derivative. This step is the chain rule. The derivative of r to the third with respect to r is 3 r squared. Solve this equation for dr dt. Then we have this equation. Now, the final step is evaluate dr dt at the instant when r is 50. When r is 50, dv dt is 20. The increasing rate of the volume is a constant, always 20. Plug in 50 in the arrow here, then this number is the increasing rate of the radius at the instant when arrow is 50. This number is 1/500 times pi. The unit is cm per second. Problem 2. Let function f be this polynomial. Part A. Find the values of x where the derivative is 0. To answer the question, I compute the derivative of function f. Function f is a product, so you can use the product rule to compute the derivative. But here, I simplify the function first. I expand the square and this product. Then function f is this polynomial. The derivative of this polynomial is this polynomial. To find the roots of this polynomial, I factorize it into these products. Now, from these products, I can see that derivative is 0 at x is 1 and x is 3. Derivative is 0 only at these 2 points. Part B. On which intervals is function f increasing? To answer this question, we need to consider the sign of derivative. When derivative is greater than 0, the function f is increasing. When the derivative is less than 0, function f is decreasing. Now, I use the points in part A to divide the domain of function f into 3 subintervals, and determine the sign of derivative on each subinterval. To determine the sign of the derivative on this subinterval, I arbitrarily pick a point from the interval, say pick 0. Then evaluate the derivative at 0, then I get derivative at 0 is positive. So derivative is positive everywhere on this interval. Therefore, the function f is increasing on this interval. Now, to determine the sign of the derivative on this interval, arbitrarily pick a point, say pick 2, and evaluate the derivative at 2. Then I get negative. Therefore, derivative is less than 0 everywhere on this interval. As a result, the function f is decreasing on this interval. Similarly, from this interval, pick a point, say pick 4, and evaluate the derivative at 4. Then I get positive. So derivative is positive everywhere on this interval. Therefore, function f is increasing on this interval. Now, the conclusion is function f is increasing on this interval and also on this interval. Part C, on which intervals is function f decreasing? This question has been answered here. Function f is decreasing on the interval from 1 to 3. Yeah, f is decreasing on the interval 1 to 3. Part D, find the values of x where the second derivative is 0. To answer the question, I compute the second derivative of the function f. Then I get 6x minus 12. Then it is easy to see that the second derivative is 0 and x is 2. Part E, on which intervals is the graph of function f concave up? To answer this question, we need to consider the sign of the second derivative. When the second derivative is greater than 0, the graph of function f is concave up. When the second derivative is less than 0, the graph of f is concave down. Now, I use the point in part D to cut the domain of the function into two subintervals, these two subintervals, and determine the sign of the second derivative on each subinterval. To determine the sign of the second derivative on this subinterval, I arbitrarily pick a point, say pick 0 from this interval. Then evaluate the second derivative as 0. Then I get less than 0. Therefore, second derivative is less than 0 everywhere on this interval. As a result, the graph of function f is concave down on this interval. Similarly, to determine the sign of the second derivative on this interval, arbitrarily pick a point, say 3. Evaluate the second derivative at 3. Then I get positive. Therefore, the second derivative is positive everywhere on this interval. So the graph of f is concave up on this interval. Now, conclusion. Function f is concave up on the interval from 2 to infinity. Part F, on which intervals is the graph of f concave down? This question has been answered in part E. F is concave down on this interval. So f is concave down on the interval from negative infinity to 2. Problem 3. In each case, evaluate the indicated limit analytically. You may use the limit laws or L'Hopital's rule, but calculator-based estimates will not be accepted. That means that you cannot use tables to find the limits. Part A, find this limit where x approaches 0 from the right side. To find the limit, I plug in 0 in x, then the limit is this number. Cosine of 0 is 1, so this number is 1 over 1. It is 1. So this limit is 1. Part B. Find this limit where x approaches 1. By direct substitution, plug in 1 in x, then the limit is this number. But this number is 0 over 0. I cannot determine it. So I turn to L'Hopital's rule. By L'Hopital's rule, this limit is equal to the limit of the derivative of the numerator over the derivative of the denominator. The derivative of the numerator, I can use the product rule to compute it. The derivative of the denominator is 1 over x. Derivative of natural log is 1 over x. Now I have this limit. To find this limit, I plug in 1 in x. Then the limit is this number. This number is e. Therefore, the limit, the original limit is e. Part C. Find this limit where x approaches positive infinity. To find the limit, we can plug in infinity in x. But then we will have infinity over infinity. We cannot determine it. Then we turn to L'Hopital's rule. This is one solution. A second solution is we can find this limit by taking out the highest power. In the numerator, I take out x squared. Then the numerator becomes this. In the denominator, I take out x. Then the denominator becomes this. Then I move x squared outside the square root. Then I have this equation. Cancel out x from the top and from the bottom. Then I have this equation. Now, as x approaches infinity, 10 over x squared will approach 0. And 30 over x will approach 0. So as x approaches infinity, this function approaches this number. This number is square root of 3. Therefore, this limit is square root of 3. Problem 4. This problem is about the mean value theorem. Mean value theorem is from section 4.2. Take a review about the theorem. The theorem says that if function f satisfies these two conditions. Condition 1, the function is continuous on the closed interval AB. Condition 2, the function is differentiable on the open interval AB. Then, conclusion. Between A and B, there must be some point C where the derivative of the function is equal to this number. For details, refer to section 4.2. Now, take a look at the problem. A car traveling along a straight road has position S of t. The units for position is in miles. At time t, the units for time is hours. For t between 0 and 1. Assume that the position of the car when time is 0 is 0. And when time is 1, the position is 60. So that the car travels 60 miles in 1 hour. In each of the following, circle A, B, C, or D to indicate the best choice available. Refer to the mean value theorem for derivatives. Part 1. We may presume that the position function S of t is continuous. The best choice is A, based on physical considerations. Part 2. The average velocity of the car during the 1 hour time interval is, I compute the average velocity here, and I get 60. So the choice is B, 60 miles per hour. Part 3. The main assertion of the mean value theorem is D. At some time between 0 and 1, the instantaneous velocity of the car was exactly 60 miles per hour. Apply the mean value theorem to this problem, problem 4. Function f is the position function, and the interval AB is the time interval from 0 to 1. Then the right side of this equation is the average velocity over the time interval 0 to 1. The left side derivative on the position function is velocity. Left side is velocity at point C. Mean value theorem says that between 0 and 1, there is a C. There, the velocity is equal to the average velocity. Part 4. The statement of the mean value theorem may be viewed as C, a guarantee that at some instant, the velocity agrees with the average velocity during the hour. Problem 5. This problem is about linear approximation from section 4.6. In linear approximation, we use a line to approximate a curve. The formula is here. The left-hand side is function f. The graph of function f is a curve. The right side is the tangent line to the curve at the point A. If you plot the graph of this function, then the graph is this tangent line. We usually name this function, the function on the right side, by L of x. Now, the problem. A differentiable function f. Differentiable function f means the function f has derivative everywhere. Satisfying function value at 1 is 3. That means that this point is 1 and 3. And the derivative of function f at 1 is 2, is approximate by its linear approximation. This approximation is this approximation. Near the point 1, 3. 1, 3 is this point. Part A. Explicitly determine the linear function L. The right-hand side of this approximation is function L. Now the point A is 1. Plug in 1 in A, then function L is this function. From the given, f of 1 is 3. Derivative of f at 1 is 2. Then function L is this function. Part B. Based on the linear approximation, estimate the value of f of 3. The linear approximation near the point 1 is this. The left side is function f, a curve. The right side is the tangent line to the curve at the point 1. In this approximation, I set x to 3, x to 3. Then I have this approximation. So function value at 3 roughly is 7. 7 is the value of the tangent line at the point 3. Here I use the value of the tangent line at the point 3 to estimate the value of the curve at the point 3. Part C. Is it possible for the estimate in part B to be exact? The answer is yes, it is possible. For example, when the curve is a straight line, then the curve and the tangent line coincide. In the case when we use tangent line to estimate the curve, the estimate is exact. Part D. Is it possible for the estimate in part B to be off by more than 10? The answer is yes, it is possible. When x is too far away from point 1, say x is 3, then the function value at 3, the value of the curve at 3, could be far away from the value of the tangent line at the point 3. Problem 6. Test so that if a car is driven at a constant speed of x miles per hour, it can be expected to travel a distance given by this function before its engine fails. Here A and C are positive constants. Part A. At what speed should the car be driven in order to maximize the distance the car can travel during its lifetime? This part A, is an optimization problem. You need to determine an x value where the function f is maximized. Theoretically, the speed of a car can be any positive number. So in part A, we need to search for an x value between 0 and infinity. There, function f has the largest function value. Because the interval 0 to infinity is an open interval, so we use the open interval method to answer this question. The step 1 of the open interval method is find critical points inside this interval. To find the critical points, we compute derivative on the function f. The function f is a quotient, so we use the quotient rule to compute its derivative. This equation is the quotient rule. A is a constant. A times x derivative is a. C is a constant. C squared plus x squared derivative is 0 plus 2x. simplify the numerator, then we get this equation. Now, to find critical points, set derivative to 0. Then solve this equation. Move the denominator to the right side, then we have this equation. Divide the equation by the positive constant a, then we have this equation. Now, from this equation, we have this equation. Take square root on both sides, then x is either positive c or negative c. Because x cannot be negative, so we reject negative c. So only one critical point in this interval. The second step of the open interval method. Sketch the graph of function f. Here I draw an xy plane. And suppose this point is the critical point C. Between 0 and C, I arbitrarily pick a point, say C over 2. Then plug in C over 2 in the x here. Then it is easy to see that derivative as C over 2 is positive. That means that between 0 and C, everywhere, derivative is positive. Therefore, the graph of f is increasing. Similarly, between C and positive infinity, arbitrarily pick a point, say 2 times C. Plug in 2 times C in the x here, then we will see that derivative at 2 times C is negative. So everywhere between C and infinity, derivative is negative. Therefore, the graph of f is decreasing. From this sketch, we can see that at the point C, the function f has a global maximum. The third step of the open interval method, make conclusion. At the speed x is c, the distance that the car can travel during its lifetime is maximized. Part B, what is the maximum distance the car can be expected to travel during its lifetime? This part essentially asks for the largest function value. The largest function value from part A appears at the critical point C. So evaluate the function f at the point C. Then we get A over 2 times C. This is the answer to part B. Problem 7. Determine the absolute maximum and minimum values of the function h, over this interval. Also indicate where these values occur. So your work justifying why your answers give the absolute extreme values of function h. Because the interval is a closed interval. We use the closed interval method to solve this problem. The first step of the method is to find the critical point in this open interval. That is, find critical points between 0 and 4. Take derivative on the function h, then we have this polynomial. Set the derivative to 0 and solve this equation. The solutions of this equation are -3, 0, and 3. So the function h has 3 critical points, but only the number 3 is in this interval. So the critical point in this open interval is the number 3. The second step of the closed interval method is to compute the function values at the critical points and also at the two endpoints of the interval. From part A, the critical point is 3. So we need to compute the function value at 3. Plug in the number 3 in the x here, then function value at 3 is -80. We also need to compute the function values at the two endpoints of the interval. Plug in 0 in x, then function value at the left endpoint is 1. Plug in the number 4 in x. Function value at 4 is -31. The third step of the closed interval method is to make conclusion. Compare these three function values. The largest is 1. So the maximum function value of the function over the given interval is 1. The location of 1 is at x is 0. And among these three function values, the smallest is -80. -80 is the absolute minimum function value of the function over the given interval. The location of -80 is at x is 3. To help you better understand the solution, here I plot a graph of function h. In this problem, we don't consider the whole graph, and we only consider the portion over the closed interval between 0 and 4. That is, we only consider this portion of the graph. About this portion of the graph, the highest point is this point, and the height of this point is 1. The location of the point is at x is 0. About this portion, the lowest point is this point. The height of this point is -80, and the location is x is 3. X is 3 is about here. Problem 8. Using the grid below, sketch the graph of a function h that is continuous on the interval 0 to 5, and that has all these properties. To solve the problem, I suggest that first, mark down all the properties on the grid below, then sketch the graph of the function. Now, mark down all these properties on the grid below. Function value at 1 is 3. I mark down this point. This point, x coordinate is 1, y coordinate is 3. This point is on the graph of function h. Function value at 3 is 0. I mark down this point. Function value at 3 is 0. Derivative is positive on the intervals from 0 to 1 and from 3 to 5. derivative is positive, the graph of function h is increasing. On these two intervals, the graph of h is increasing. Mark down this information. From 0 to 1, the graph of h is increasing. From 3 to 5, the graph is increasing. Derivative is negative on the interval from 1 to 3. Derivative is negative. The graph of h is decreasing. So from 1 to 3, the graph is decreasing. Second derivative is positive on the interval from 2 to 5. Second derivative is positive. The graph of h is concave up. From 2 to 5, the graph is concave up. Mark this information down. Second derivative is less than 0 on the interval from 0 to 2. Second derivative less than 0. The graph of h is concave down. From 0 to 2, concave down. Now I have marked down all the informations. Next, I sketch the graph of function h. I sketch the graph piece by piece. The first piece is from 0 to 1. Over this interval 0 to 1, the graph is increasing and concave down and passes through this point. So the graph on this interval looks like this curve, increasing, concave down, and through this point. The second piece is from 1 to 2. On this interval, the graph is decreasing and concave down. So the graph decreasing, concave down. The third piece is from 2 to 3. Over this interval, the graph is decreasing and concave up and passes through this point. So the graph looks like this curve, decreasing, concave up, and through this point. This point is a point of inflection because the curve changes concavity at this point. The curve changes from concave down to concave up at this point. So this point is a point of inflection. The last piece is from 3 to 5. Over this interval, the graph is increasing and concave up. So the graph looks like this curve, increasing, concave up. This is a sketch of the function h that satisfies all the given conditions.